As a test for conflict serializability, we're going to construct a data structure called a conflict dependency graph. And in this dependency graph, there's going to be one node for every transaction in the system. Okay? And there's going to be an edge from transaction Ti to transaction Tj, an ordered edge. If there's an operation Oi of Ti that conflicts with an operation Oj of Tj, and Oi appears earlier in the schedule than Oj. So it's an ordered edge, it's ordered by time, and it's between two transactions with conflicting actions. And the theorem says that the schedule is conflict serializable if and only if its dependency graph is acyclic. It has no cycles. Okay? And as a sketch of a proof, think about this. Conflicting operations can't be reordered. Remember on the previous slide we could swap non-conflicting operations, but conflicting operations can't be reordered. And that prevents us from swapping the operations in a schedule with a cyclic conflict dependency graph to get a serial schedule. So let's see an example of that to make this point more clear. We're going to build up a schedule here that is not conflict serializable. We'll start with two transactions, T1 and T2. And T1 is going to begin by doing a read of an object A and a write of A. And then T2 is going to come along and do a read of A. And that read is a conflict with T1's write of A. So now we have an edge from T1 to T2 in our conflict graph. Next, transaction T2 is going to do a bunch of other operations that don't introduce new edges. There's a write of A, which is already conflicting with T1's write of A using the same order of operations. So that's covered. And then a read of B and a write of B, neither of which conflict with any of T1's operations. And then finally, we're going to have a read of B in T1, and that conflicts with the write of B in T2, which came first. So there's an edge from T2 to T1, and that creates a cycle in the conflict graph. Now, when you look at this schedule of T1 and T2, try to swap things so that T1 comes first. You can't, because that read of B on the upper right does not swap with the write of B on the end of T2. So that write of B has to stay where it is. It can't move to the left. So can we swap T1 to be further towards the right? No, we cannot, because the write of A in T1 will not swap with the read of A or the write of A in T2. So we can't move the write of A to the right. We're stuck here, unable to form a linear order of T1 and T2. And this is why the cyclic dependency graph prevents us from getting a conflict equivalent serial schedule.